This is Jensen Joshua Lim, and this is Physics 2211 Lab 4 Oscillations. So the purpose of this lab is to understand and predict the motion of our system, which in this case consisting of a spring, a mass, and the Earth. So we'll be looking at the predicted motion with the observed motion of a mass attached to a spring. So it's important to note that the system in this case would be the mass, spring, and the Earth, whereas the surroundings would be nothing. And by the end of the lab experiment, we could prove that the total change in energy would be zero, and the predicted model and the observed model are relatively similar to one another. Some important concepts that we're going to be looking at is Newton's second law, which includes the change in momentum over time, and we can see that the total net force in this experiment particularly, we'll see the total spring force as well as the total gravitational force would be equal to the total net force. So the total net force therefore will be negative k multiplied by the change in length of the spring multiplied by L hat and the addition of the gravitational force mg delta y. Some other important concepts will include the energy principle. So the energy principle states that the change in energy of a system is equal to the work done on the system by the surroundings and the exchange in thermal energy between the system and the surroundings. It is also important to note that energy can never be created nor destroyed, however it can be transferred from one form to another. So you can see the total energy of the system should be equal to zero. So in this case, we're going to have kinetic energy, spring potential, as well as gravitational potential energy. And other equations that we'll be looking back again will be the velocity update formula, as well as the position update formula. And the formulas for kinetic energy would be half mv final squared minus v initial squared. Gravitational potential energy will be mgh, and the spring potential will be half ks squared. So the first part of the experiment would be video analyzing a spring. As you can see that the object mass starts at 0.402 kilograms and the length of the spring is 0.7 meters. And the initial position and the initial velocity is given right there. And after you track frame by frame of the spring's movement, you receive the graph at the bottom from the tracker software.
So we'll do that for the same for the code where you just plug in all the initial values like the ball mass, the initial positions, and the ball velocity, as well as your gravitational constant, spring constant, and the relaxant. So this is the code for the system of energies, which includes kinetic energy, gravitational potential energy, and the spring potential energy. So this is a code for the while loop to estimate the spring's position. So once we've calculated the total F net, which is through the spring force and the gravitational force, you can use that to substitute into the velocity update formula and then into the position update formula. And after including all your kinetic energy formulas, your spring energy formulas, you'll be able to determine the position of the spring mass.
Once we've completed our code, we will input a Excel file which consists of the positions that we obtained from the tracker software through the video analysis. And this is what we get from the code. And as you can see, the X position and the Y position is sinusoidal, and the model and experimental shape is relatively similar. And if you look at the bottom left graph, you can see that the X and Y are sinusoidal shape. You can also see that the total energy remains at zero, meaning total energy is conserved and there is no change in energy. Some possible errors to take into account in this experiment is, in reality, the system is not isolated from the surroundings, so there will always be work done from the surrounding itself. And the initial velocity, it's not supposed to be at zero, but it should be a non-zero value, but because this is unavoidable. And some other forces were not taken into account during this experiment, and there could be some inaccurate placement on the tracker while doing the video analysis. So throughout the experiment, is the energy principle satisfied? Yes, the change in energy is always zero throughout this experiment. As you can see here from the graph, as I mentioned previously, the total energy adds up to zero, which indicates that the total energy is conserved. And how do the positional estimates per oscillations compare? So the two graphs below shows the x versus time graph and the y versus time graph. And how we can obtain the time difference is by taking how long it takes for one period and you compare between the x and y. And by doing that, you get 1.615 seconds and 1.519 seconds. So from this, we can conclude that the lower the difference between the time, the more accurate the spring potential will be, because this difference can also account for external forces such as air resistance. So that is another error that we can take into account for the time difference.